Let us start lecture number 12, and this will be the last lecture of this module, that is a converter analysis. And this lecture will be addressed towards the converter chart, and in this chart we will see the AC quantities of network side, and also we will see if we will change the axis. Like in the previous lecture I discussed that if your axis are your voltage and current, then we draw the various quantities, that is the DC quantities alpha, delta and U. And today again on the same axis we'll see the characteristic that is called the network side. Means we are going for the AC quantities. AC quantities in the network side, although so many are the dependent to each other, but we can say that it is a three different one. One is your displacement factor, another is your power, and another is your current, that is the AC side. In the power we are having the three different powers: apparent power, real power and reactive power. No doubt the two can give the third one. That means they are the dependent, so only the two are independent. Here I am going to draw the displacement factor, not it is your simple power factor. So to know the difference between the power factor and the displacement factor, as its name, the displacement means it is the first we have to define what is the displacement angle. Displacement angle is the angle between the voltage phasor and the fundamental component of current, that is angle is called the displacement angle. You know, it is only the displacement factor is valid if your loads are non-linear or you are having some power electronics load. Then means there are some harmonics are also appearing along with the fundamental. So the displacement factor is basically angle between V, that is you are applying the source, in this case this Vp, and then you are having V1 and it is a phase current. One is your fundamental component of the current which is flowing in that AC side. So the angle between this, basically we are, if it is angle is 0, what is angle here? If it is phi, and then cosine of this angle is known as the displacement factor. We know this is another component here, I1. If you remember, it is the RMS value. Here I am not going to write 1. It is basically RMS value of all the components that is added together. So this is, you know, it is defined as this RMS, the total RMS I am talking, which is suppose having a current having so many harmonics, including fundamental, fifth, third, whatever you can say. So this one is your RMS. It is nothing but your I1 square plus all the components of this. But here we are taking only this component. So you know always this value is larger than your this value. It may be equal if other harmonics are 0, so we are going to have the same. So it is your cosine of this angle between the voltage, because we are injecting the sinusoidal voltage. There is no voltage harmonics in AC side. AC side we are having the source is a balanced three-phase supply. Only the current is having harmonics, and that's why we are having the fundamental component of that phase current, and the angle between these two is displacement angle and the cosine of this. So it is defined the cosine of angular displacement between the fundamental component of AC line current as well as associated line to neutral voltage. This is the phase voltage. And now the power factor, as I said, if you are not having the harmonics, this will be the same, and then it is defined. So the power factor is basically the ratio of input power. Input power, always we are talking about the fundamental here power which is coming to this source. So the input power means that is your V1, means that is already Vp here in this case, because we don't have any harmonics on the voltage side. So we are having the I1 RMS here. Basically we are talking here in terms of, you can say simple RMS here, and this is your RMS which is written in this expression, and here the displacement factor. So this is your input power, that is the fundamental component power corresponding to that is taken from the AC side, divided by the volt ampere. The total VRMS here divided by here IRMS. So this value is always, you can say this value is always larger. So the power factor is less than your displacement power factor, because this value here you can see I1 RMS divided by IRMS. I1 RMS, again that I said this is the first component here. In this case it is RMS here. So the ratio of these two, you can say always here this value is less than unity. So the power factor is further worsened, and this is called your displacement power factor. So whatever we derive in our expression, I am coming to that equation here, we are going to draw the AC side quantities. I will come here, if you see the displacement power factor here, that equation we derive in terms of cos phi is equal to y and other things. Here again, I just remind you, here Vd upon Vdo, we are taking it as y, because we are drawing the voltage, per unit voltage on your here y axis. So this is your, I can say Vd prime. So this is your Vd prime, means your this axis, and your x axis here your Id divided by IS3, and it is your x, or I can say Id prime, means it is in per unit, because you are dividing by here the base value and you are getting the per unit here, and this is your Id prime, or you can say it is x axis. So already we draw for the DC quantities. If you remember, we draw for our constant alpha, constant delta, and the constant u. Already we saw the characteristic. Now in the AC side, we are going to draw these things: real power, current, again is the AC current, here displacement factor, apparent power, and also we are going to draw the reactive power. Now see how we are going to derive all these expressions. First one, let us say, as I have written here, it is your real power. We are believing the real power which is coming out the converter is equal to the AC side, because it is, we are assuming your transformer as well as your converter is lossless, is ideal case. There will be some loss, no doubt, but we are assuming here, that's why the per unit power in the DC side is equal to the per unit power in the AC side. That is ideal case, and we are drawing here all the characteristics for ideal case. So we know we are going to draw here the PAC, that is the AC side in per unit, that is equal to your PD in per unit, means it is your VD per unit multiplied by your ID per unit. And already we know this is your nothing but it is y, here it is x, means we are having x into y characteristic. And that's why here it is written the PAC is equal to x into y here. If your x is varying, accordingly for the given AC, what will be the y value or x value, that we can draw. Another is your current. Here this your current IAC prime, here it is, I am saying it is equal to your ID prime, and it is your x. How it is true? How? No, current cannot be based both sides. It is not guaranteed, it is not necessary, because you know here what we are taking the voltage on your primary side, what is the base value? If your AC side base, it is your power. Here DC side we are having the same power, here the PD. The base value is same both sides. Power is the base both sides. Now you have to see what is the voltage different from the rectifier end and this end. So that will be the not same, because the base value this side it is your V phase base value, but this side it is your VDO. Just you see it. So the base value here this side, here this, now we have to calculate what will be your current base here based on these two AC side. Similarly we can have here ID prime, we are taking the base, that is here, that is your base value is IS3. To calculate this value, we can go back to our, we can write what is this expression is valid, and from here we can derive it. Now what is the PAC? Just we can, this is true, here it is equal to your XY. Okay. Now what is the PAC? PAC we are talking here is under root 3. If you are talking 3 line to line, or it is better to write 3. Your V phase into your I AC, what we are talking the phase value, that is your cosine phi, this is the power, 3-phase power, is equal to your here PD, but here you remember it is not a PD prime. This is your PD because the AC power is equal to your DC power. Once you are going to divide this multiplied by this value, then that will be the PD this side. So this is, I can write it is your VD into your ID. Okay. Now from here we can write this VD and your ID here. So what we are going to get here? The VD we can write in terms of, I think we can define here the displacement factor here first, and then we can go for this one. First we can derive here this expression because ultimately we are reaching here because the cos phi here, then we will go back to I here, hardly matter. Or we can go back again. Now you see this your I1, RMS is how much? We can derive from here already IAC. I1 we derived, it is under root 6 by pi into ID. We have derived this. This is the fundamental component of, that is a 6 pulse converter current, here the DC current which is flowing in the link. Now your ID prime, this IS3, what is this your IS3? It is root 3 EM upon twice omega L. So to derive this, we can go back with this cos phi, and I think it's a better option. So first what we can do, we can just define this value here in 3-phase form and just put this value here. This is IAC is nothing but this value here. So we can write here 3V phase into your under root 6 by pi into ID cos phi. This value is your VDO cos alpha plus cos delta by 2 into your ID. Just from here I want to derive this first, the power displacement factor, and then we'll come back here in the current, that is easier. Now this ID is cancelled here. Now you see what this value. This value is equal to this value, only VDO. Just put this value, you can see how much you are getting. This is 3 under root 3. This is multiplied by root this VM divided by pi, and this is your EM, and this is your nothing but your VDO. Okay, this 3 under root 3 I have taken, this V phase here is RMS value, so the under root 2 is multiplied here is your peak value, that is your VDO. Now what we are getting from here, your cos phi is equal to 1 by 2 cos alpha plus cos delta. And this already we proved earlier also. In this case only what will happen, all this here, the value which we are taking here, this is the case when it is the ideal case. This component was derived when there was no overlap. But due to overlap, this value will be not equal to that value, it will be slightly changed. That's why I can say this is approximately equal to this value. Remember, this value we derived in the ideal case when the current was changing like this, if you remember. But due to the overlap, what will happen? This will be changing. And due to this change, this current fundamental component will also change. This will affect, and that is, error is very small, and finally we can get this expression that is very equal to this value. Now this value, what is this? This is related to your, just remember this, your VD expression. Here we write here. So this value is nothing but, I can write, this is a cosine phi. It is your VD prime simply. Means this value is nothing but your VDO here. Because we wrote this expression, if remember this VD is equal to VDO cos alpha plus cos here by 2. So if this value you are divided here, VDO, means you are having this value. And this is nothing but VD prime. And the VD prime is nothing but your Y. So the displacement factor is just equal to your Y in the per unit sense. Again, everything we are talking now in per unit. So this is also, this value is always less than unity, and this is the per unit, so it is unity itself. So this is your, this factor already I have written here for the displacement factor. Now we have to come back here for I. To equate this, we have to use the same equation here. Now, this is the case when we are just writing, if you are writing here the VLL or something, this is a three-phase power, this is a total DC power. Now, here what I am going to do in this case, the cos phi already we have defined, it is a Y. So here if I can divide by VDO prime here, here also I can divide by VDO here. So this is your Y, and this Y is cancelled out. So I can say this is removed, and this is I am also removing. Now here if you are going to make this value, and now here this is I1, basically your IA prime in the per unit value, we have to now take the base here, and it will be nothing but your ID prime, and it will be your X.
Sir,
You
equated AC power equal to DC power.
Yeah.
But in AC power, we should not take fundamental component. We should take whole current.
Look, if you are writing in the per unit, here the same expression we can write here, the V AC prime, the per unit value, voltage per base, into your current base here. We are talking about the current base here, everything in base. Here cosine phi is your VD prime. It will be more easier to understand this. The per unit power in the AC side will be equal to per unit power in the DC side.
That is fine, sir, but that IAC would be.
Listen now it is here I have changed that equation. Here it is I am tracking prime, means per unit value. So per unit voltage, per unit current multiplied by power factor, because this is a VA per unit, multiplied by power factor here, it is your active power in the per unit. And that AC PAC prime here, basically now I can say PAC prime here. So in per unit the three phase concept has gone, it never appears. Because the simply the per unit here, if you are taking line to line, the base will be the line to line. If you are taking the three phase power as a base, then voltage will be your line to line base. So that ratio, the under root 3 and 3 terms appear in the per unit system. Simply if your base is 100 MVA base, you multiply this and multiplied by 100, it will be actual power, that is three phase power. So here now I am writing in the this value, so there is no question. Now this value is your X into Y. This is also your Y, IAC prime here, and this value is the voltage base, and this voltage base is basically given. Your power base and the voltage base are assigned, then your current bases are calculated. In any per unit quantities, you require, basically there are the three quantities: power, voltage and current. The two are the dependent, one is automatically calculated. So in any per unit system, normally this power, this is basically apparent power, whole transmission system, the active power and the MVA almost same. So this power and this power voltage is base value is defined, I base is calculated. So in this case, voltage base here is your unity, because the divide by the same actual value with the your base value, this becomes unity at all. So this is your cancel here, this is cancel, and your IAC in per unit, it will be your X. So it is easier to define. Otherwise, we have to go for the calculation of here the base quantities. We'll see this whole base quantity conversion when we'll talk about the AC/DC load flow. Because once you are going to deal with the AC/DC load flow, you have some problem. Yes?
So you are taking
Here?
VAC prime cancelling over.
No, it is unity.
Okay.
This is, I am telling what is the VAC. VAC means actual voltage divided by your the base voltage. And that is your base voltage, so it is unity. So this is unity. I am not saying it is cancel. So it is unity. So here we are getting this value, means I can say 1, and then we can write this X.
So the problem is that while deriving cos phi equals to 1, you took cos phi equals to y.
Yeah.
You
In the per unit, yes.
Yeah, you took
We define this.
Yeah, you took IAC equals to the fundamental component of.
At that time, I didn't use in the per unit.
Yes, sir. But why would IAC be only the fundamental component of the current?
Here also, I am talking about the fundamental component.
Sir, exactly this was my question.
Sir,
Here we are not taking this. We are here still we are talking this fundamental component.
Sir, why we are taking only fundamental component?
Because here other components are very less. They are the filter out so many components, 5th and 7th, that is not coming to the network side, and other components are very, very less. So this chart is approximate. Here we are talking 1 only for the fundamental component, because this is also true for fundamental component only. Here we are using the displacement factor. It's not even the power factor. That's why I here use Y. Otherwise I cannot use even Y, because that would be different value. It depends upon the power factor. So we are talking about the AC side. What happens? All the components basically gone down, the filtered out. So we are having this AC current here, that is equal to your X. Now this apparent power here, apparent power in the per unit. Again here is a prime I am using. So this will be equal to your EA, that's voltage prime, the per unit, into current prime. EA again is unity, and IA already is I derive X, so it will be X. So apparent power is also X. Now the reactive power, we know this per unit, this apparent power is square minus your real power is square of under root. And then you have to put this value here X, here XY square. You are going to get here X outside under root 1 minus Y square. So these are our 5 quantities that we can draw on our this axis. And this chart is now known as the AC side quantities on your voltage and current axis. So here again we are having here this ID prime, here we are having VD prime or Y. Now we can draw the first one, leave the first one first. We can draw first the displacement here. Here the displacement you can say is equal to your Y, means for the given displacement here phi value here, the Y is constant, means at that axis this is a constant throughout, so it will be all this. Here both sides of the voltage. This is negative side, here I can say 0.5, here unity, here minus 0.5, here minus 1. Before drawing this, we know what is the actual operating range of this converter. We had the various boundaries. Here if it is 1, if you remember, then we got 1.15 for more than U is 60. Then we had the characteristic here, that is your alpha is equal to 0. We had a characteristic here, that is delta is equal to 0. No, delta is equal to 180. Then we found there is another slope here, that is your alpha is equal to 30, and here delta is equal to 150. So here, if you remember, we found one point here where u was 60. Here another point was there where u was 60. And between these 2 points, it was your u is equal to 60 curve. So hold this converter chart on voltage as well as the current axis. We are having the 3 zones. On the first half, it is alpha is equal to 0. Certain value here it was A, here it was a C. Then we are having the u is equal to 60 operation, and then we are having this operation alpha is equal to 30 in this zone. So our characteristic here will be confined to only in this zone, because we cannot operate our converter beyond this zone. So this is the boundary of our operation, means it cannot, here alpha is 0, here is 80, then if you are going u is 60, then you can go here, this is a limiting factor, and finally if you are exceeding 60, then your this zone comes. So this line, which is horizontal line, and all both rectifier operation here as well as inverter operation, it is the parallel to your x-axis, and that is your displacement factor going there. Now question arises, what is the value here and what is value here? This value here, this is nothing but your cos phi, means here the power factor is 0, here the power factor is unity. It's obvious. If you are operating alpha is equal to 0, your power factor becomes unity, because already we defined where u is 0, here u is 0, and then it's a actual operation ideal condition. So this is your positive side and this is negative side of y. As per definition here, we are getting this. Now second characteristic we can draw here, this IAC. IAC here is x. For constant value of IAC, x is set. Means if you have 1 per unit, here you can say 0.2, means x is 0.2 all the time. So we are having this vertical axis. So this axis means these lines, that is vertical lines parallel to your y axis, that correspond to your this apparent power and the current. So here these lines are apparent power, I can say apparent power, and your IAC prime 1. Here again it is IAC 1. Now we can draw this PAC. It is a equation of hyperbola, inverse characteristic we can get, and we'll find here it is like this characteristic. Means once your P is here, at this point once your P is 0, we are here. Means P is 0, means you are either x is 0 or y is 0. So P 0 means either you are here or you are here. For other than that value, it is your increasing, means your P is increasing in this way. Means from 0 it is 0.1, 0.2 and so on and so forth you are increasing. Here also your P, that is the P prime, what we are talking, PAC, here PAC. Now what will be the characteristic of this? See, this characteristic you can just, means here it is x 1 minus here y square, it is a, it will be the characteristic of similar to this one, and I can draw from here, and it is nothing but we are going to get this value here. This is your Q. Means Q is 0 this side and you are moving this side. So this is your Q characteristic on the same curve. Now to see it, you can just see in here in this graph. You can see from here we are having this is a Q characteristic here, Q, more Q, and here you require less Q. And that is also true if you are operating here, your power factor is in this here, it is a better. So if Q is 0.0 here on this axis, then you are going keep on increasing. If you are operating here in this, as I said, if your alpha is increasing because alpha is changing here, if you are coming this side, alpha is more, power factor is worse. So this is the Q, this is your P axis, P curves on this axis, and these are vertical lines are your apparent power and the current AC side, and this is your cos phi, that is the displacement factor. So this is related to your AC side quantity, and now we will move to your another quantity that is called another chart. Here instead of voltage and current, sometimes we require our axis should be in the power, because it is not always possible that we can see whole things on the voltage and current axis. It is also better to have the power axis, so we have to reverse this curve because here P and Q are there. So we can have Q on our y axis and P on your x axis, and then we can draw all this quantity again further, but that chart becomes very, very complex. So let us see what are those quantities, and then we can define it here. Means in this chart what I am going to do, it is we are taking x is equal to P prime, here again prime in the per unit sense, and then we can have the apparent power, then we can have the displacement, then we can have the constant U, constant alpha, constant delta, current, all the curves we can draw in this axis. And to draw it here, the apparent power is very clear. This is x square plus y square because P and Q is square. But for others, it is as difficult and as complex, because to go for the U term or even the alpha term, delta term, it is very, very complex. But we have to go for first the displacement, and then other things just I'll derive and I'll show some of the things. So now I am going to draw this active and reactive power on as well other parameters, other quantities on this chart. Before this, even though last turn we were discussing about this angle is alpha here, delta is 150 degree. This constant basically is similar to this constant because alpha, which I said it is not less than 30 degree. Here it is your delta cannot be greater than 150 degree. The reason is same because if you see this in 3-4 valve conduction mode, here I said if it is your EBA is your commutation voltage of valve 3, it was not possible because only after 30 degree this voltage was positive across valve 3, and that was your EBA. So this was 30 degrees. Similarly here this side, this must be over before the 30 degree here because the voltage is going to reverse. And once its voltage is going to reverse, means here you have to fire your beta, and then there will be some U, so that it should not here go beyond 150 degree. So this your delta basically is 150 degree, means alpha plus beta here. So this case you can say this is alpha 30, here it is not alpha 150 degree, it is a delta 150 degree. Because we are concerned here because it is going to change from here. So it is your beta, then there will be U degree, so beta plus U is basically your delta. So here basically this is the concern is 30 degree, means 180 minus 150 degree. Now let us draw the AC side quantities. Here this one, and first I'll draw what will be the displacement power factor. You see the displacement power factor here, this curve. Now this circle showing your apparent power, because here in this axis we are drawing your P prime here, here it is your Q prime, means this is your X, this is your Y, and in this case what is done, it is both side of the here we are going for this now the P positive and negative, and Q we are talking here only this is positive side, but it can be also the 0 down as well. So it is drawn in the such a fashion I can say it is your P, because P negative means P positive means it is a rectifier, that is the flowing inside to DC link, and negative means it is inverter operation. So your S is nothing but your P square plus Q square. So it is a equation of a circle, means that is your X square plus your Y square, and the radius is the value of operant power. So your operant power is if it is changing here, it is your circle. Of course, if it is going in Q side negative, so it will be going this side as well. But always your this operates that requires the reactive power support, whether it is a rectifier, so it is a lagging power factor. So this is your operant power characteristic. This is the circle. This is your P. This is your 0, is the positive side, here negative, and this is your Q. Now the displacement factor, you see this is a straight line. Now how to calculate the displacement factor? Here it is displacement factor, that is your cos phi. It is nothing but is defined as active power if you are talking the per unit. So this is your per unit value divided by your operant power per unit. And this value is your X. This is your under root X square plus Y square. Now from here, just simplify it, and I want an expression in terms of X and Y. So here if you are going to multiply here, simply square it. So we are getting here cos square phi, here X square plus Y square is equal to your X square. Just I squared it here. So I can write your Y square will be your X square 1 minus cos square phi. Okay, and no, here I am missing something. Here cos square phi. So if you are taking this under root, means Y cos phi is equal to your X sin phi, means we are having Y is equal to your X tan phi. So for a given phi angle, means power factor, we are having a straight line of Y and X. Here this is a fix, and then we are varying. Means if your power factor is, now we can draw for the different value. If your P of displacement factor is your, we start with the 0, then your phi is your 90 degree, and here if you are going back here, we are getting the power factor unity, here phi is equal to 0. Now if your power factor is unity here, now what will be the value of tan phi here? Huh? It will be 0, and 0 means your Y is 0. So you are here somewhere. The power factor 0 here means it is infinite, or reverse means your X is 0, here you are here. For the any other values, it is a straight line, because this is a slope. Any value of phi here, that is calculated here, you are having, this is the straight lines, starting with the origin. And this characteristic here, that is strong. You can see here the power factor is unity, and the power factor is keep on deteriorating till here 0, and then it is going the different lagging side depending on the, because power reversal is there, but reactive power requirement is still there.
So you mean displacement factor?
Displacement factor, yeah. Here we are talking in whole displacement factor, because the power factor is very difficult to calculate because so many harmonics are there. So here still we are talking the this phi is the displacement factor. Here in whole this converter circuit, I didn't talk about the power factor, although I use the power factor because it is very close to that. So this is your operant power and your this value displacement factor. We also know this operant power, yes, is very equal to IA, that we remember it was x in the per unit sense. The apparent power per unit is your the V per unit AC into here AC per unit, and this is unity. So this was this. Already x we defined, means here it is also x square into y square in the per unit. So your apparent power as well as your current, AC current, will be the circle. That's why it is written here the apparent power and the current equations, because both will have the same type of characteristic. No doubt the value here will change. For a given value of IA, this value will be decided. So here the current and apparent power, and we draw for the displacement factor. So we have drawn all the quantities, all the 5 quantities, except our VD and ID on this plane, because we want to draw our VD as well, that is VD prime, and your ID prime. Now what will be your VD prime, VD this, and this it is approximately. This VD prime and this is the VD prime will be approximately here your cosine phi. To remember, cosine phi is equal to, I wrote y when it was the VD prime. When I was drawing on the VD current and voltage axis, this was y here. So means that was equal to your VD prime. So VD prime is approximately equal to here the displacement here again, because the overlap angle is we are not considering, that's why I am writing here. So you can see this is a cos phi here, and this is nothing but a characteristic similar to your displacement factor. Means that's why here you can see written on these scales here the displacement factor and the direct voltage. So these straight lines are showing your, these slopes are showing your the displacement factor as well as the direct voltage in per unit. These circles are showing your apparent power and your current on this one. Now another quantity here, it is your ID prime. ID prime, it was nothing but it is also related to your S, because again we define here S from ID power here, and this is your x square plus y square here, means this is again apparent power. So here it is written current, apparent power and the power factor, displacement factor, all this. Here this straight line is apparent power basically, and you can see we have just derived. The major problem in this one, if we are going for alpha, delta and U characteristic, because converting U in terms of power and apparent power is very, very tremendous. It's very complex here. Let us see here. See this. Now, mathematically we can derive equation first very simple for constant U, because for the constant U, if you are going to derive from all this basic equation, you will find you are getting an expression similar to a circle equation, which basically is, which here the diameter or this distance is your radius is keep on changing, and it is touching your the 0 axis, it is passing from here. Means all these are the circles. Here this is a stretch, so slightly it is not looking circle, but it is circle, because here I think this graph is stretch. If you are going to do this, it is circle. So the equation for this, for the constant U, if you derive, it is very complex. It is your nothing but which is coming out to be your x square plus your y minus your U by 2 square, and here your sine U by 2 square. Now you see here is not sine, it is actual value, and this derivation is, of course, it's very complex, and that's I don't want to derive it again. Here only I can show you this is a characteristic here for the given u is here less 5 degree, 10 degree, 20 degree, 30 degree, and here up to 60 degree. If you are going for more than that, this characteristic again becomes a different. Now if you will see, the scenario becomes very worse for the alphas and the deltas. It has a different characteristic. Again we can derive it is very complex for the different plane. That's why the normally charts are used for the voltage and your current axis. Or if you are going for the AC side, normally what we need, if you are analyzing your converter from the DC side, always it is beneficial to use your current and voltage axis chart. If you are deriving in this AC side, it is better to have the P and Q because we talk about whole system in the real and reactive power and voltages. So this is better in that side. But if you are going for the DC side, just you can see it here, what complex, even though drawing the chart is very complex. Now if you go further here, now this is basically it is another curve for the ID and other values. It is going to be very complex here. Here slightly in this case what we have done, this axis here basically your is exact compared to the previous one. Here we are drawing the ID prime and the VD prime, but here we have taken very care here this the VDs are changing with the axis here VD, and the currents are this one. So this chart again it's very complex. That's why I said if you are going for this DC side quantity alpha, U and delta, these values on the PQ axis, it's a complex chart. So if you are going for the DC, because the P and Q is AC side, Q always comes in AC. In DC there is no Q. So I can say the DC variables on the AC axis is not good. And the same time, if you are having the AC variable on that side is also not good. So it is better to use this PQ chart for the AC quantities, and the DC you can use your voltage and current. So in this, so this chart is over, but now I have to summarize what we did in the 12 lectures. Here in the summary, if you will see, I devoted so many lectures here. First lecture was basically for the single phase rectifier circuit. It was starting with the half wave rectifier, then we went for the full wave rectifier, again the center tap transformer, then we used the bridge circuit, then we introduced the commutation value, this commutation group Q, and then in the second lecture I started with the three phase rectifier circuits, and we used the grouping, how the Q, the commutation group was decided, that the Q value. We also introduced the R and S, that is the series and the parallel. We derived the voltage equation for those three phase simple circuits, rectifier circuit. Then in the lecture number 3, I started to go for what should be the exact better configuration of converter circuit. In that we saw the various features. We derived the 4 features, that we should have the highest the DC voltage, harmonics are highest ripple we should go for, the transformer utilization should be better, and also the peak inverse divided by your DC, that the peak inverse voltage I can say in per unit, it should be the less as minimum as possible. Based on that, we decided that for the 6 pulse converter, and I gave assignment for the 12 pulse converter to you, and that we decided which configuration is better, and the final doing some modification in that optimal selection. If the same winding is used for the twice, so the winding factor was improved and the transformer utilization is improved. So that's why we use the bridge circuit, that is a grid circuits. Once after deciding this, we went for in the lecture number 4, it was a converter circuit analysis. Then I used the very ideal conditions for the bridge circuit inversion. I used both your rectification as well as the inverter operation. In the ideal case, when always the 2 valves were conducting, one from upper limb and one from the lower limb. Then in lecture number 5, I just introduced if there is some overlap as a practical circuit. We also defined the various voltages at that time, what will the phase voltages, line to line voltages, and then I went for this U less than 60 degree, what will be the conduction mode, and then we saw our rectification operation in the 2-3 valve conduction mode. That was in lecture number 6. In your lecture number 7, I introduced the inverter. I just saw the graphs, output voltage for the inverter operation of 2-3 valve conduction, and then we also introduced about 3-4 valve conduction mode. In lecture number 8, we derived the various voltage and the equations corresponding to the changeover from valve 1 to valve 3 or from 3 to 5, and then we derived the various instances for the currents, etc. And that was also in the lecture number 8. In lecture number 9, I introduced another that is called, already this gamma was coming out all the way till our 3-4 valve conduction mode. Then I introduced another variable that is the zeta, and this was your commutation margin angle was defined, and for various ways that we say in inverter operation how this angle both are changing. So it depends upon the dent. In lecture number 9 also I discussed about the 12 pulse operation. We saw how this, and we also draw the valve voltage corresponding to the delta winding of the transformer. If the delta winding is there, then how we can draw the output voltages, we define clearly. In lecture number 10, I just give you 5 problems. I explained those 5 problems. Those were related to your quiz as well as it was related to your mid-sem 1 examination. And lecture number 11 and 12 were devoted to your chart. It was related to your, first I went for the DC side variables. I defined the chart for the DC variables, that is your alpha, U, delta, VD and ID. And in this 12, I just went for the AC side, and also we saw this, we are changing the axis, means we are going to draw whole chart on the real and reactive power axis, then how this becomes very complex. And just I defined for you only AC side quantity exactly. For the DC side, I showed it is very complex and that's not required at all at this level. If you are doing some research or something here, then again this huge mathematics is involved. And then with this, I can disclose this module 2, lecture number 12. In the next module, we now will use our voltage equations, and then we'll go for the control objectives, how we can control our HVDC link, what should be the various options. We'll also see what is the role of OLTC transformer. OLTC means online tap changing transformers. As I said that these HVDC links are always connected with the OLTC. It is not a normal transformer. They are having the tap changers. They are keep on changing the voltages that is required by the DC here. First we try to control the voltage by your converter circuit. If this converter limit is hitting, then the tap changer start changing. So we'll see how this control philosophy is done and what will be the control characteristic for both rectifier and inverter side. One will be trying to maintain your current, then we'll go for, even though this value minimum value, alpha minimum value, so many characteristics we'll find, and then we'll see what are the various control schemes or philosophies are being used. That we'll see very clearly in that your control operation. So with this I should end it, and if you have any doubt, of course, if there is no doubt, then we can end it here. Thank you.